Hi, in this video, we will discuss the concept of polygons. So the discussion of the polygon starts with that what exactly do we call a polygon? So here comes the definition. In element geometry, a polygon is a plane figure that is described by finite number of straight line segments connected to form a closed polygon chain or the polygonal circuit. So let me just put it forward in the simpler language. Polygon is a closed loop of various sides. So the number of sides can vary starting from 3. So the minimum number of sides that a polygon can have is equal to 3. And if we have a 3-sided polygon, we call it a triangle. If we have a 4-sided polygon, we call it quadrilateral. 5-sided polygon, we call it pentagon, and so on. So now we have to understand that what are the basic variety of polygons that we come across. So we have categorized the polygons into these two broader categories. The first is called the regular polygon and second is called the irregular polygon. Now the way to define the regular polygon is quite simple. A regular polygon in the simplest language can be called a symmetric figure, a symmetric from all the dimensions of it, which means if it's a triangle and if you see it from all the three sides, it should look exactly same from all the three sides. If you look at a quadrilateral, it should look exactly same from all the four sides. That means in case of triangle, an equilateral triangle is a regular polygon. In case of quadrilateral, a square will be a regular polygon. So if we have to define what a regular polygon is, we can say that the polygon which has all the angles equal as well as all the sides equal, then we can call it a regular polygon. If a polygon has only the angles equal, then we cannot call it a regular polygon for sure. For example, see in the irregular polygon, the very first category, you see a rectangle. A rectangle has all the four angles equal, but since the adjacent sides are not same, so we can't call it a regular polygon. So I reiterate, a regular polygon is one in which all the angles are equal as well as all the sides are equal, because all the sides are equal in isolation again does not ensure that it's a regular polygon. For instance, you can take an example of a rhombus. A rhombus has all the four sides equal like this figure, but it's not a regular polygon. So for the polygon to be regular, both the conditions should be met. That means all the angles should be equal as well as all the sides are equal. If any one of the conditions is not met, then we start putting it into the category of irregular polygons, right? So irregular polygons, all angles are not equal or all sides are not equal or one of the two things is not meeting the criteria, then we call it an irregular polygon. Another way to define the polygons is depending upon the measure of their angles. So we can also call the polygons in two categories. One is called the convex polygon and the second is called the concave polygon. So convex polygon is simply a polygon in which all the angles, interior angles, basically we are talking about the angles between the two adjacent sides inside the polygon. If they are less than 180 degrees, then we start calling the polygon as convex polygon. For the discussion of the GMAT problems, convex polygon is the only polygon that we might be interested in. Concave polygon is the polygon in which somewhere we get a reflex angle. For example, here if you see the angle is greater than 180 degrees, it is 270 degrees. So such a polygon is called concave polygon, and concave polygon does not fall in the purview of the discussion of GMAT. So here what we are going to discuss and what we are not going to discuss from the GMAT perspective can be categorized this way. We are interested in the convex polygon and we are interested in the regular polygons. What we are not interested in are concave polygon and irregular polygon. So now that we have cleared our objective of the discussion, now we can proceed further and discuss a little more about the polygons. Alright, so let me quickly take us to the next slide, and the next slide will get us well acquainted with the variety of polygons, which means what are the polygons that we may come across when it comes to the discussion of GMAT. So we discuss a 3-sided polygon which is triangle, 4-sided polygon which is quadrilateral, 5-sided polygon which is pentagon. So we need to know what a pentagon means. It means the 5 sides, hexagon means 6 sides, heptagon means 7 sides, octagon means 8 sides, nonagon means 9 sides, and decagon means 10 sides. So these are the terms that we may expect in the questions of GMAT, and we need to comprehend the terms when they are visible in the questions. Now, taking the discussion forward, I would like to take an example of a polygon and would like to discuss the relationship among the angles that exist in a polygon. So for instance, I'm taking the most frequently used polygon by GMAT, that is a hexagon. So assume that it's a regular hexagon, a regular six-sided polygon. In any regular polygon, we can see that there are two angles that we can find in a polygon. One is called the interior angle. Interior angle is the angle drawn between the two adjacent sides. And second is the exterior angle. Exterior angle is the angle when the side is extended outside the polygon, then the angle formed outside is called the exterior polygon. So one relationship that's very clearly visible here is that interior and exterior angles are supplementary, which means their sum is equal to 180 degrees. Now here I would also like to give a reminder that sometimes the question does not talk about interior or exterior. It simply says what is the angle measure of a polygon. Now the question is, what angle does the question expect from us, whether interior or exterior? Then just look at it from this perspective. If somebody asks you what is the angle measure of a regular triangle, which means what is the angle measure of an equilateral triangle, we always answer the question in a way 60 degrees. We never say 120 degrees because we like to answer the polygon's angle as the interior angle. The interior angle in an equilateral triangle is 60 degrees while the exterior angle is 120 degrees. So we always mention by the term angle of a polygon as the interior angle. Now, since we have assumed that it's a regular hexagon for the discussion purpose and for bringing in certain properties, so I would like to discuss a way how to derive the relationship among them, because the derivation that we are discussing is quite application based derivation, and therefore the discussion of this derivation is very important rather than just putting forward them in terms of formulas. What I'm going to do is, if we draw a line AD, do we realize that line AD will divide this figure into exactly two identical parts, and the line AD will also pass through the center of the polygon? The answer is yes, because now if we start drawing the lines, I mean the diagonally opposite corners, we start joining it, then all these lines will pass through the center, and that will be the center of this regular polygon. Which means if you are standing here and looking at the side BC, or whether you are standing here and looking at side AB, the scene will look exactly the same because it's a regular polygon. Now, these sides, because it's a regular figure and it's a symmetric geometry around these green lines, so we can say that line AD will bisect the interior angle at point A, which means the interior angle here will be divided into two equal parts, and the parts will be I by 2, where I is representing the interior angle, right? So now if we understand this, then we can see that everywhere this I will be divided into two equal parts, and everywhere we can write I by 2, I by 2. Now for bringing in another perspective, what we do is we take the triangle OAB, assuming the center is O, and we look at this triangle OAB. Then we have to come up with an observation that triangle OAB is a triangle in which three angles should sum up to 180 degrees. So that's what we have written, I by 2 plus I by 2 plus x is equal to 180 degrees. Another thing to mention is, if we say that this angle is x, then every other angle at the center should be x, because it's a regular polygon and we are looking at the same kind of figure every side when we stand here, right? So now the relationship that we have is that in this triangle OAB, the sum of the three angles should be 180 degrees. So I by 2 plus I by 2 plus x should be equal to 180 degrees. Now we have these two equations to compare with. Let's call it equation number 1 and let's call it equation number 2. Now the comparison is really very important. The moment we start comparing these two, we see that this I by 2 plus I by 2 together will make equal to one interior angle. And similarly, these 180 are equal on the other side. So these are the few observations that we already have. And since the two equations are being compared, so we understand that this x eventually should be equal to the exterior angle. And this observation is very critical for our calculations and for the ease of our calculation. The moment we acknowledge that the angle drawn at the center is going to be equal to the exterior angle, now we can quickly find out the measure of each exterior angle, because here, since we have taken a six-sided polygon, so this entire angle at the center has been divided into 6 equal parts, which means if we take an n-sided polygon, then the entire angle will be divided, this 360 degrees at the center will be divided into n equal parts. And then we can say that the value of each exterior angle is equal to 360 over n, where n is the number of sides. Now, there are two important things to note here. First is the property that each exterior angle can be calculated by dividing 360 by the number of sides that the polygon has. Secondly, and this is essentially only in case of a regular polygon, not in case of irregular polygon, because an irregular polygon can have various numbers as representing the exterior angles, because there every exterior angle can assume a different value. Now the second thing to focus on is that everywhere we have the same angle distributed x. So the x is equal to exterior angle, which means when we calculate the exterior angle, it's completely up to us whether we write the exterior angle outside like this or whether we write the exterior angle inside at the center like this. Now, here I would like to just suggest that looking at the information and the required output by the question, we have to understand that where should we write this value of each exterior angle. In many cases, writing the angle outside makes sensible, whereas in many other cases, writing the angle at the inside is also important. So what I do to be on the safer side is when I calculate this angle and when I draw the figure while solving any question of polygon, I always represent the angle at both the places and then I see where do I have to utilize the value of this angle. But from here, now we can proceed quickly and then we can find out the value of each interior angle as well basing this, because we already understand that the sum of interior and exterior angles is equal to 180 degrees. That means the value of each interior angle can be called as 180 minus exterior, which is 180 minus 360 over n. So once we have this angle, we can calculate the interior angle immediately, which once again is very useful. In case of a regular polygon, we often have to divide this into two equal parts by joining the vertices of the polygon with the center of the polygon. Now that we have the measure of each interior angle, which is a measure which we can calculate only in case of a regular polygon, because in irregular polygon, every interior angle may have a different value. Now from here we can proceed further and we can find out the sum of interior angles as well. Now let's quickly look. How many interior angles do we see in the figure? One angle is at point E, one angle is at point B, one angle is at point C, one at B, one at A, one at F. That means at each vertex we have one interior angle. That means for an n-sided polygon, we will have n interior angles, and therefore the sum of the measure of all the interior angles in a polygon can be represented by one interior angle multiplied by the number of sides, which is n. So this gives us 180 multiplied by n minus 2 is the sum of the interior angles. Now, there is one important observation that I would like to take your attention to, and that is when we are talking about the sum of interior angles of an equilateral triangle, then we say that the sum is 180 degrees. Now I say suppose the triangle is not equilateral, it is something else. Let's say it is an scalene triangle. What will be the sum of all the interior angles in that triangle? The answer is once again 180 degrees, right? Which means the sum of the interior angles is not dependent on the polygon being regular or irregular. Similarly, if you take any quadrilateral, whether it's a square or not a square, the sum of all the angles of the quadrilateral will be 360 degrees, because it has nothing to do with the polygon being regular or irregular. It's only dependent on the number of sides. Therefore, we can generalize that sum of the interior angles can be applied for the regular polygons as well as for irregular polygons. However, these two can be applied only for regular polygons and not for irregular polygons. Now, the way we understand the sum of the interior angles, exactly in the similar fashion, we can find out the sum of the exterior angles as well, and that will be equal to one exterior angle times the number of sides, and that becomes 360 degrees, which means certainly it has nothing to do even with the number of sides. Irrespective of how many sides the polygon has, the sum of the exterior angles is always 360 degrees. But the only important point to note here is when we say sum of the exterior angles, we always extend all the sides in only one direction. For example, this side FE we have extended only in the anti-clockwise direction. So we will extend all the sides only in the anti-clockwise direction, and all the exterior angles that we see in the figure, they will add up to 360 degrees. That means this is, let's call it number 1, then this is angle number 2, this is angle number 3, this is angle number 4, angle number 5, and angle number 6. The sum of these 6 exterior angles will be 360 degrees. So all the sides are extended in only one direction when we find the sum of exterior angles equal to 360 degrees. These are 4 important properties that we need to know, and irrespective of what the question is asking, every question of polygon requires us to calculate the value of exterior and interior angle at first. So the last and the most important suggestion in the case of polygons is that at any point of time when you come across any question of polygons, the first thing that you're supposed to do is to calculate the value of each exterior angle by dividing 360 by the number of sides. And from here, we can quickly calculate the remaining 3 things if needed. But certainly the calculation has to start from the calculation of each exterior angle. And if we are thinking about solving the question without calculating the angles, I'm afraid either it will be difficult or we might fail to answer the question at all. So always remember, start the calculation from the calculation of each exterior angle, each interior angle, and then see how the question proceeds. We will see that in a couple of examples that we will discuss during this course. Thank you so much for watching this video.